Welcome to Part 6 of the Introduction to Inference. We're going to review the margin of error. The margin of error, which we're going to denote as E, in a whatever percent confidence interval, in which sigma is known, is given by the formula, the critical value Z alpha over 2, which is determined by our confidence level, times the standard error of our sampling distribution of the sample mean for samples of size n. As we stated earlier, the margin of error determines the width of the confidence interval. It's going to 2 times the margin of error will give you the width of the confidence interval. Now, there are 3 factors which determine what the width will be: the confidence level, the sample size, and the standard deviation of our population. Larger sample size, smaller levels of confidence, and a smaller standard deviation reduce the margin of error, reduce the width of the interval. Now, there's not much we can do with the standard deviation, but there are things, as we said, we can do with the sample sizes and the confidence level to manipulate how large or how small we want the margin of error. Now, just a quick caution, the margin of error does not cover all errors. The margin of error is a confidence interval, covers only random sampling errors. No other source of variation or bias in the sample data influence the sampling distribution. Practical difficulties such as undercoverage and non-response are often more serious than the random sampling error. The margin of error does not take such difficulties into account, so beware of these points when reading any study results. So let's look at a problem. We're going to look at travel time. An urban economist wishes to estimate the mean amount of time people spend traveling to work. So he takes a random sample of 50 individuals who are in the labor force and finds that their mean travel time is 24.2. For the problem of estimating the population mean amount of time people spend traveling to work, assuming the population standard deviation of travel time is 18.5 minutes. What is the margin of error for a sample size, 50, and the level of confidence, where the level of confidence is 95%, and then determine the effect on the margin of error of increasing the level of confidence on the confidence interval to 99%. So, to calculate the margin of error for a 95% confidence interval, well, first of all, we know that the margin of error for the 95% is the critical value times the standard error divided by the square root of times standard error. That, in this case, for 95% confidence interval, the critical value is 1.96. We were given a population standard deviation of 18.5 and the sample size of 50. So our margin of error is 18.5 divided by the square root of 50. I multiply that by 1.96 and I now have the margin of error, 5.13. So the whole width of the confidence interval would be twice that, or 10.26. Now let's determine the effect on the margin of error of increasing the level of confidence on the confidence interval to 99%. Well, the margin of error for the 99% confidence interval, remember what the margin of error is, the critical value times the standard error. Well, the critical value for a 99% confidence level is 2.575. And the standard error is going to be the population standard deviation of 18.5 divided by the square root of the sample size. So that'd be the square root of 50. I do that, I multiply those all together, and I get 6.74. Now the whole confidence interval then would be twice that. 13.48. So what was it? When we increased our confidence level, the margin of error increases. So when we're planning study, choosing the sample size for a particular confidence level where we want a specific margin of error or a margin of error no more than a certain amount, we have a way to do this when we know what sigma is. The confidence interval for the mean of a normal population will have a specified margin of error, we'll call it M, when the sample size is, and this is how we determine it. Basically what we're doing is we're taking the calculation for the margin of error and we're solving it for n. So now we can put in for confidence level or critical value, we'll know what sigma is, and then we divide by the particular margin of error we want. We take that, and we take that critical value times sigma divided by that margin of error, and then we square that quotient. That will give us n, the sample size that is needed such that we'd have that confidence level with that particular no more than that particular margin of error. Now if the n turns out to be anything but an integer, then we have to go to the next greatest integer. So something like if n was 12.112, then we'd say our sample size would have to be 13. So you go to the next greatest integer if your sample size calculation is anything but an integer. So it's time to look at an example. Now back to the NAEP scores. Suppose that we want to estimate the population mean NAEP scores using a 90% confidence interval, and we're instructed to do so such that the margin of error does not exceed 3 points. And recall that in that problem the population standard deviation was 60. What sample size will be required to enable us to create such an interval? Well, we take our calculation for n and then we just plug in the numbers. So if we want a 90% confidence interval, our critical value is 1.645, sigma was 60, and we want a margin of error of no more than 3. So we use 3 as our margin of error. We do that quotient, product divided by 3, and then we square that and we get 1082.41. So, since that was not an integer, we go to the next greatest integer to ensure the confidence level that we want with the margin of error that we want. So, we would say that we need 1083 in our sample size. Another way to say that is we need a sample of at least 1082.41 men aged 21 to 25 to ensure a margin of error not to exceed 3 points. Now, since we can't sample a fraction of an individual and using 1082 will yield a margin of error slightly more than 3 points, our sample size should be 1083. As we said, you go to the next greatest integer to ensure the confidence level that you want with the particular margin of error that you would like. Now it's time to begin testing our parameter value. So we're going to start talking about tests of significance, hypothesis testing. And the first thing we have to do is learn a little bit of vocabulary. We need to determine the null and alternative hypothesis from a claim and state conclusions to the hypothesis test. Now, hypothesis testing is just another part of inferential statistics. Hypothesis testing and estimation are two different approaches to two similar problems. So estimation is the process of using a sample data to estimate the value of a population parameter. That's the confidence intervals that we just did. Whereas hypothesis testing is the process of using sample data to test a claim about a value of a population parameter. So hypothesis testing is the setup of our problem is that we want to determine whether a particular claim is believable or not. This is one of the most important goals of statistics. Now the process we use is called hypothesis testing or tests of significance. So we have a parameter value. A claim is made against that parameter value. We need to gather some evidence, and we're going to have to do that through our sample data, and it's collected to test the validity of the claim. The data are analyzed to assess the plausibility of the claim, and the conclusion about the claim is stated. So hypothesis testing involves learning how to state our claim in terms of values of a population parameter. That's relatively easy to do. And quantify how confident we are in our claim. Now this requires our inferential statistics. So similar to estimation in the previous chapter, we will again use the material for sampling distributions of the sample mean for sample proportions to quantify how confident we are in our claim. And that's not chapter 8, that's chapter 11. So in our next installment, we're going to continue with hypothesis testing.